For many centuries, Aristotle's fame rested on his early works, which were written as dialogues, similar to Plato's famous works. Unfortunately, these works have been completely lost. What we have today are essentially just his lecture notes, and it's only by serendipity that we have even those. You see, after Aristotle's death, these notes went to his friend and successor at the Lyceum, Theophrastus. But when Theophrastus died, he didn't leave them to the Lyceum. He left them to his nephew, who apparently didn't pay them much attention. And when he finally died, his heirs sold them to Ptolemy Philadelphus, who was building up the famous Library of Alexandria, which we'll get to soon enough. But they were afraid that the rest might be taken by Attalus of Pergamon, who was busy building up his own library in Pergamon. So they hid Aristotle's notes in a cave. Later, a rich book collector got word that Aristotle's notes were hidden in a cave in the area. He managed to find them and added them to his own private library. This book collector died shortly before the Romans, led by General Sulla, sacked Athens in 84 BC. Sulla then carried the books back to Rome, where Andronicus of Rhodes prepared a first edition of the books for scholars to read. And those books are presumably the same ones that we still have today. It just goes to show you how haphazard the preservation of books from this time was, that what I'm about to tell you about Aristotelian physics depended on such a winding route. So what do these notes contain? As I said in the previous episode, Aristotle was a man of diverse interests, from physics to biology to art and everything in between. He was also the son of a doctor, and his most impressive accomplishments were probably in biology, not physics. Let me give you a couple of examples. To understand the development of an embryo, he had the idea to take a bunch of bird eggs of known ages, so one freshly laid egg, a one-day egg, a two-day egg, and so on, and then break them and examine them to determine when the organs formed. He found that depending on the kind of bird, the heart first appeared around day 3, which he concluded by finding a little speck of a beating heart. He also examined the stomachs of animals like cattle and sheep, and correctly concluded that their stomachs had 4 chambers. He has quite a bit more to tell you about biology, both good and bad, but this is a series about physics, so I'll have to leave it at that. So let's have a look at what he has to say about physics. Aristotle came up with a whole system of physics we call Aristotelian physics. It's all wrong, nearly every last bit of it. But as I've said, you get points in physics for the correct method. But also, much of what he taught actually seems kind of right and agrees with our intuition. And this was the starting point which became dogma over the centuries. In fact, the history of modern science begins with the rebellion against Aristotle, which is a large part of why we must talk about him to understand the history of modern physics. First, he separates the universe into 2 parts, the celestial, which means the moon and everything above it, and the terrestrial, which means everything below the moon. Observation shows us that the terrestrial region is full of birth, death, and transient changes of all kinds. It's messy. The celestial region, on the other hand, is orderly. The heavens have a regular repeating motion, and observations over many generations from many different cultures indicates that the heavens are unchanging. Sure, from hour to hour it changes, but the same motions keep repeating themselves in a regular, orderly fashion. Aristotle agreed with his predecessors that there are 4 elements: earth, water, air, and fire. But he expanded on this. Each one has its natural resting place, and if allowed to move naturally, they will each move toward their natural resting place in a straight line. First comes Earth. Earth's natural resting place is at the center of the universe. If you take a piece of Earth and let it go, it will move in a straight line to the center. In other words, downward. Next comes water. Water's natural resting place is above Earth. If you mix Earth and water together, the Earth will eventually sink to the bottom, and the water will rise to the top. Then comes air. Air's natural resting place is above the water. If you try to force air below water, the air will come bubbling back up to the top. Finally, we come to the 4th element, fire. Its natural resting place is above the air. When you light a candle, you can see the flames reaching up, trying to rise up above the air. And so in the terrestrial region, everything has a natural upward or downward motion. The only way things move horizontally is if there is some external forced push or pull. Left to their own, all matter will move straight up or straight down to its own resting place and stop there. Furthermore, when something made of earth falls downward, its speed depends on its weight. The heavier the body, the faster it falls. Of course, this, like most of everything else I'm explaining here, is wrong. But the speed of a falling object also depends on the medium the object falls through. The denser the medium, the slower the fall. So when you drop a rock through the air, it falls quickly. When you drop it through water, it falls more slowly. Aristotle then reasoned that if you got rid of the medium altogether, so that you were dropping your rock through a perfect vacuum, there would be nothing to hinder the rock's fall, and it would fall infinitely quickly. When you dropped a rock, it would instantaneously be on the floor, meaning that the rock would be in 2 places at once. This is nonsensical, so clearly a vacuum can't exist. Or so Aristotle thought. This takes care of natural motion, but clearly things also move when we push or pull them. You could call it unnatural motion, or forced motion. Well, Aristotle thought that all motion required a mover. In the case of natural motion, the mover is the nature of the body itself, moving the body to its natural place.
You drop it? We'll drop it. You ready?
When the body reaches its natural place, it stops. With forced motion, you are the mover, or something else that pushes or pulls the body with some force. And motion ceases as soon as the force is withdrawn. Furthermore, if you apply a force to some body, it will move with a certain speed. And if you try to push a body that's twice as heavy, Aristotle claimed that you must push twice as hard to move it at the same speed. So far, so good. I mean, this is all wrong, of course, but at first glance, at least, it seems reasonable and consistent with our everyday experiences. But there's one thing that kind of sticks out as an obvious problem. What about projectile motion? If motion ceases as soon as the force is removed, shouldn't a ball just drop straight down when you release it? How can you do something as simple as throw a ball? The truth is that the ball keeps moving even after it's left your hand. Aristotle's answer was that the medium does the work. When you throw a ball, you transfer to the air the power to make it move. Once the ball has left your hand, it's still in contact with the air, which keeps moving it along. Here, let's watch that again. Now, if this seems a little contrived to you, you're not alone. This would be a weak point in Aristotelian physics for a while, and several later philosophers and scientists tried to fix it over the years. So by this point he had addressed how things move here on Earth, but when we look to the sky, to the celestial region, observation tells us that things move completely differently. The sun, moon, planets, and stars don't move up and down, they move around us in circles. So in the celestial realm, including the moon and all above it, everything must be made of a fifth element, quintessence, or ether. The natural motion of ether is to move always in constant, uniform, circular motion. You can hear Pythagoras and Plato's influence here, can't you? But Aristotle wasn't really all that comfortable with much Pythagorean teaching. Do you remember the Pythagorean notion of the harmony of the spheres? That's the idea that the planets make a hum that depends on their distance from the Earth, similar to the way the pitch of a plucked string depends on the length of the string, and that the combination of these planetary hums is a beautiful harmony. Aristotle argues forcefully against it, and I want to explain why, because it's a good example of how Aristotle tries to use observation to separate good theories from bad. He tells us that the Pythagoreans believed that the planets must make loud noises because of their speed and size. But we just don't hear them because we were born and raised around it. Sort of like a fish who doesn't notice that it's surrounded by water. We're oblivious to the sound because we're just so used to it. But, Aristotle argued, loud noises shatter solid bodies. Thunder splits rocks. If the planets make a noise, it must be even louder because of their great size and speed. Yet we see no rocks splitting and no objects vibrating. Indeed, we see no evidence of a loud noise anywhere. Well, Aristotle seems to say, what's the difference between a harmony that no one can hear, with absolutely no effect on the world, and no harmony at all? And so we see here Aristotle getting us a little closer to the modern scientific viewpoint that observation is the final arbiter of truth. That the way to sort the good ideas from the bad ones is to look at the world and see which ones work and which ones don't. Having dismissed the harmony of the spheres, Aristotle then turned his attention to determining the order of the heavenly bodies from the earth. Okay, so the heavens are characterized by perfect uniform circles, and the earth is characterized by birth, death, and change, and just generally imperfect motion. As we saw in episode 4, the fixed stars seem to go around the earth once every 23 hours, and 56 minutes, over and over, forever, with no apparent change. They have the simplest and fastest motion of all the heavenly bodies. They must be the most celestial of all celestial things. So Aristotle put them farthest from the earth. All the other heavenly bodies move more slowly and have more complicated motion. Going by their apparent speeds, he next placed the planets, then the sun, and finally he placed the moon closest to the earth. But Aristotle wasn't completely happy with this arrangement. He offered up his own objections. You see, a lawyer argues in order to win, but a scientist argues to clarify, to get closer to the truth. And so they have no reason to conceal the weaknesses in their arguments. A good scientist happily points out the weaknesses in their own argument in the hopes that someone else can help figure it out. The main problem is that the fixed stars move in simple circles. The motion of the moon is a little bit more complicated, but then the planets, which Aristotle correctly believed to be between the moon and the stars, move with the most complicated motions. If the stars, with their perfect motion, are the farthest from the earth, shouldn't the most complicated motions be reserved for the bodies that are closest to the earth? Shouldn't the planets be closer to the earth than the moon in this case? But Aristotle knew that the planets have to be farther than the moon. Again, he knew this from observation. He pointed out that many different cultures over many years have seen Mars pass behind the moon. And not just pass behind the light part of the moon, where you could be mistaken, but pass behind the shaded part of the moon, where Mars is shining bright one moment, then blinks out as it passes behind the moon. So clearly, Mars is farther than the moon. So this was bothersome to Aristotle, and he guessed at possible reasons, but mostly he urged greater research into this puzzling question. Now what about the question of the Earth's motion? Is the Earth stationary, as most philosophers believed? Or is it in motion, as Philolaus believed? If you'll recall from episode 3, Philolaus had come up with a theory in which the Earth circled around the central fire once a day, and he used this to explain why the stars appear to circle overhead, among other things. Aristotle comes down firmly on the side of those who believe that the Earth is at rest, and he explains his reasoning. First off, Aristotle thought he had already addressed how things move. There's a point in the universe we call the center, and the 4 terrestrial elements move to their natural resting places relative to it. That reasoning seems to explain why heavy objects like rocks fall downward, while light objects like air and fire move upward. And so, according to theory, the Earth should simply be sitting at rest at the center of the universe. Aristotle was very clear. Rocks don't fall toward the center of the Earth because it's the center of the Earth. Rather, they fall there because it's the center of the universe. If we were to somehow move the entire Earth a little to the right and let go, the entire Earth would fall back to the center of the universe. And the Earth can't be moving unless there's some force pushing on it, which would have to be a very large force indeed, and which just seems absurd. So as far as theory goes, it's clear. The Earth must be at rest at the center. Of course, his laws of motion were wrong right from the start, so this argument doesn't work at all. But he didn't know that. However, Aristotle also looked for empirical signs of the Earth's motion. First off, we see no stellar parallax. So what exactly is parallax? Imagine you're sitting at a table, and before you are a wine bottle and a glass. If If you move your head from side to side, the bottle appears to move to the left and to the right of the glass. Of course, the bottle isn't moving, you're moving, and your vantage point relative to the bottle and glass is moving. But the bottle and glass are just sitting there. But they appear to move, and that apparent relative motion is called parallax. So what does that mean for the motion of the Earth? Well, if Philolaus is right, and the whole Earth is revolving around a central fire, then let's imagine looking out at a star that's in front of us. At one point in the Earth's orbit, the star will appear in front of us and to the left. But as the Earth moves around the central fire, the star eventually ends up in front and to the right. And as the Earth goes around and around, the star's position will seem to shift. Left, right, left, right. So just like the bottle and glass, Aristotle argued that if the Earth is really moving around the central fire, then the positions of the heavenly bodies should be moving relative to each other, from our point of view, every revolution. Here, take a look. It's not just that the stars appear to be moving around the Earth. They seem to be moving left and right, and getting closer and farther as the Earth moves around in a circle. That simply doesn't happen in real life, though. All the stars keep their positions relative to each other, as if they were just painted up in the sky like some kind of heavenly wallpaper. This is why we call them the fixed stars to begin with. They appear to be fixed in the sky. So the Earth must not be moving. Furthermore, if the Earth were moving, then we should notice it in objects that are dropped and thrown. When you throw a ball straight up, no matter how high, it always comes back down to the same point. But if the Earth were moving, Aristotle argued, the ball should land somewhere off to the side, because the Earth moved while the ball was in the air. Here, let's watch that again. Sandy throws the ball, and it moves straight up, and meanwhile, Sandy and the rest of the Earth move out from underneath it. So this seems to indicate that the Earth must be standing still. Now, the truth is that stellar parallax really does occur, but the stars are just so far away it's a very small effect, as we'll see later. And Aristotle's notion of natural motion was wrong to begin with, so none of these arguments work, but they seem eminently reasonable at least. Next, Aristotle tackled the question of the shape of the Earth. He argued that it's a sphere, which of course it is. The Pythagoreans had believed it was a sphere too, but we can't say for sure why they thought that. And knowing their penchant for mysticism and their belief that circles and spheres were the most perfect shapes, it's quite possible the only reasons they had were aesthetic. But finally, with Aristotle, we have someone who will tell us why they thought the world was round. Aristotle began with a theoretical argument. He believed he had already established the correct laws of motion. In particular, he believed things made of earth travel toward the center of the universe. And if everything falls to the center, the resulting shape will be a sphere. But then he added some observational evidence. First, he knew that lunar eclipses were caused by the Earth's shadow falling on the moon. And if you watch a lunar eclipse, the shadow appears round. Aristotle reasoned that it's hard to have the Earth's shadow always show up round unless it's a sphere. I mean, if the Earth were flat, then you'd expect that at least some of the time you'd get a weird-shaped shadow on the moon. Furthermore, by this time, there had been many astronomers who had traveled large distances and kept track of the stars in the sky. If you keep traveling northward and always watch the sky, you'll notice that new stars begin to appear on the horizon. There are some stars that are only visible in the north, and some other stars that are only visible in the south. Here, this is the night sky facing north near Heliopolis, Egypt. And this is the sky near Cyzicus in northern Turkey. You see how the stars are shifted a little farther upward in Cyzicus? This is hard to explain if the world is flat. I mean, let's picture a flat Earth with a dome over it, like a snow globe as we saw back in episode 1. If you're standing in one spot, you'll look up and see a particular star. Then if you move far away, that star will appear in a different location, but the stars on the horizon will never change. You wouldn't see new stars as you walked around. You'd just see the same old stars in different positions. If the Earth is round, though, it makes perfect sense that as you go north, you start to bend over the Earth's curvature, and new stars become visible. At one point, there will be a particular star that you can't see because it's below the horizon. But as you walk around the Earth, it becomes visible. In fact, Aristotle says that the mathematicians tell us that the Earth has a circumference of 400,000 stadia. Unfortunately, he doesn't say who these mathematicians are. We can only guess. Perhaps it was Eudoxus and his student Callippos. As we saw in episode 4, Eudoxus was a meticulous astronomer and studied the skies at different observatories located far from each other. But whoever it was, how'd they do it? And how big is a stadion anyway? Well, I could give you some ideas about how someone might have estimated the Earth's size in Aristotle's day, but I won't, because Aristotle doesn't tell us. Instead, you'll have to wait until we get to the story of Eratosthenes to hear about the first person to measure the size of the Earth and tell us how he did it. As for the size of 400,000 stadia, that's about 70,000 kilometers, or 44,000 miles. The correct answer is closer to 40,000 kilometers, so it's at least in the ballpark. It makes you think that whoever made that measurement, and however they did it, they must have been on the right track. As I've said, almost all of Aristotle's physics was wrong. To Aristotle, every object had its nature, and to study it, you must observe it behaving naturally. Unfortunately, that tends to rule out controlled experimentation, one of the cornerstones of modern science. But his works were still a large step forward from what had come before. His theories weren't merely myths repeated uncritically, nor were they just beautiful mathematical stories that were chosen simply because they were aesthetically pleasing, as the Pythagoreans' theories seemed to be. They were general principles based on real observations of the world. But he didn't appreciate how tricky and subtle nature could be. He wasn't as meticulous in his observation as he ought to have been, and he came to his conclusions too quickly. And in the end, He was so persuasive that his theories became the straitjacket that bound medieval thinkers for far too long. It was only once we could break free of him that real progress in physics became possible.